This video is about the fundamentals of logic. This is the first module in the course Discrete Mathematical Structures for 4th semester BE in VTU. Course code is BCS 405A. So the topics I am going to cover here are proposition, logical connectives, tautology, contradiction, contingency, conditional statements and their converse, inverse, contrapositive statements, logical equivalence, laws of logic, rules of inference, methods of proofs and disproofs. So what is proposition? It is a declarative sentence which is either true or false. So here we have few examples. We will decide which of them are propositions. 2 plus 3 equal to 5. This is true. 2 plus 3 equal to 6. This is false. 3 is not a prime number. This is false statement. 7 greater than or equal to 10. Even this is a false statement. So in these 4 examples we are able to decide whether they are true or false. Hence they are called propositions. Now what do you think about x plus y equal to 12? Is it a proposition? Here we don't know what exactly x and y represent, whether they are complex numbers or real numbers or matrices. We have no idea about x and y. So unless we know, we cannot tell correctly whether x plus y is equal to 12 or not. Hence in this case it is not a proposition. 13 is an unlucky number. It may be true or it may not be true. It is just a belief or an opinion. So even this is not a proposition. Now starting with any given proposition, we can create new propositions and also make compound propositions using the words like or, and, if then, if and only if. Such words are called logical connectives. So there are few logical connectives we'll see. First one is negation. So suppose P is any proposition, negation of P is not P and it is denoted by this symbol. The symbol used is this. So here for example P is a proposition 4 is less than 9 and negation of P will be 4 greater than or equal to 9. You can also write this in another way. 4 is not less than 9. Even this is negation of P. Now we can write the truth table for negation. P has two truth values. It can be false, it can be true. If P is false, then its negation will be true. If P is true, its negation will be false. If we denote false by 0 and true by 1, we can write the truth table in another way using zeros and 1 like this. So here afterwards we will write the truth tables using zeros and ones. Conjunction is nothing but combining two propositions using the word and. So conjunction of two propositions P and Q is written as P and Q. Inverted V is the symbol for and or conjunction. Suppose P is the proposition code compiles, Q is the proposition code runs correctly. Then the compound proposition P and Q will be code compiles and code runs correctly. To write the truth table for conjunction, the rule here is so conjunction P and Q is true only when both are true. So in the last row you can see both are true, then hence P and Q is true. In all other remaining cases, if any one of them is 0, then AND will be 0. Disjunction of propositions P and Q is P or Q. So here we are combining two propositions P and Q using the word OR, which is logical connective. And the symbol used for OR is small v. So symbolically we write this as P or Q. P is the proposition, user is admin. Q is another proposition, user is moderator. P or Q is user is admin or user is moderator. Now how to write the truth table here? P has two truth values 0 and 1. Q has two truth values 0 and 1. So totally there are 4 possible truth values for P and Q 0 0 0 1 1 0 1 1. So P or Q will be true if any one of them is true. If both of them are 0, then P or Q will be 0. So the rule here is P or Q is true if any one of them is true. Next is conditional statement. It is of the form if P then Q. If P then Q. So P and Q are two propositions. We are combining them using the words P if then. And the symbol used is arrow pointing towards Q. We are to read this as if P then Q. Here P is a proposition, it is raining. It is raining. And Q is the proposition, I carry an umbrella. So the conditional statement will be if P then Q. After if insert P, after then insert Q. So conditional becomes if it is raining, then I carry an umbrella. Now to write the truth table, again we write the 4 possible values of P and Q 0 0 0 1 1 0 1 1. So the conditional statement will be true always except this one. Except this. When the first proposition P is true, but the second proposition Q is false, only here it fails. So 1 0 becomes 0. This is very important result. Please remember this. Because we are going to use this in proving the conditional statement by indirect method. Few more examples on conditional statement. In this one I have taken 4 propositions P, Q, R, S. P is 2 is a prime number which is true. 6 is multiple of 3, it is true. 6 is a perfect square, no, it is not true, it is false. 2 plus 5 equal to 8, even this is false. So what is the truth value of the following conditionals? First one, if P then Q. So P then Q. Here we know P is true, so its truth value is 1. Q is also true, its truth value is 1. Now look at this table. If both of them are true, then the conditional is true. So this conditional is true. Now second one, if P then R. P is true, truth value is 1. R is false, so its truth value is 0. So 1, 0. Look at this table. 1, 0 gives you 0. It means this conditional is false. Its truth value is 0. Third one, if R then P. R is false, P is true. Here, first proposition is false, second proposition is true. So 0, 1 we have, 0, 1. So this conditional will be what? True or false? It is true. Next, fourth one, R then S. R then S. So both of them are false, 0, 0. So when you look at this table, if both the propositions are 0, then also the conditional will be true. So this is true. Its truth value is 1. I hope you understood this. Next is biconditional. Biconditional is nothing but it is a compound proposition made of two conditionals like this. If P then Q, if Q then P. These two conditionals are combined using AND. And the resulting proposition becomes the biconditional. P if and only if Q. The symbol used is arrow pointing both sides. So if P then Q and if Q then P is written as P if and only if Q. So the truth table shows here. So when this biconditional will be true, if both P and Q have the same truth value, either both of them are true, then it is true, or both of them has to be true, then also it is true. If one is true, one is false, then it becomes false. So these are 5 main logical connectives. Next we'll go to tautology, contradiction and contingency. Tautology means it is a compound proposition which will be always true, irrespective of the truth values of its primitive propositions. For example, prove that for any propositions P and Q, the compound proposition not Q and if P then Q, then not P is a tautology. So this all together is one compound proposition. We have to find its final truth value. If we get always 1, then we say it is a tautology. So first here we write the 4 possible truth values of P and Q. So next we need here if P then Q. So one column is there, if P then Q. And here we require not Q. So not Q column is here. Then these two are combined using AND. So not Q and if P then Q, I have denoted it as R. Then right side is not P. Lastly, we have to connect this proposition using conditional. So now let us fill this table. If you are familiar with the conditional statement truth table, so where it fails, only here. 1, 0 becomes 0. You have to remember this result always. In rest of the cases, it is 1. Now we'll write negation of Q. 0 becomes 1. 1 becomes 0. 0 becomes 1. 1 becomes 0. Now R is combining this column and this column using AND. 1 and 1 is 1. 1 and 0 is 0. 0 and 1 is 0. 1 and 0 is 0. So first column has P. So now I will write negation of P. It will be 1, 1, 0, 0. So now I will connect these two propositions using conditional statement. So where it becomes 0, only when we have 1, 0. We don't have such possibility here. So 1, 1 becomes 1. 0, 1 is also 1. 0, 0 is also 1. 1, 1 is also 1. So this compound proposition is always true. Whatever is the truth value of P and Q, finally it becomes true. So hence we call this as a tautology. Contradiction means just opposite of tautology. It will be always false. So a compound proposition which is always false is called a contradiction. One simple example is P and not P. It is a contradiction. Very simple example. So P is 0 and 1. If P is 0, negation of P will be 1. If P is 1, negation of P will be 0. So when we combine these two columns using AND, 0 and 1 will be 0. 1 and 0 will be 0. So it will be always false. So this is contradiction. And lastly, contingency means it is a compound proposition which can be either true or false, depending on the truth values of its components. Converse, inverse and contrapositive statements of if P then Q. If P then Q is a given conditional, for this we can write its converse statement as reverse of this. If Q then P. This statement is called the converse of if P then Q. Then inverse of this conditional is not P then not Q. And not Q then not P is called the contrapositive statement of if P then Q. All of them are different. They are not same. Write the converse, inverse, contrapositive statement of the conditional. If user is authenticated, then user can access the dashboard. So here is one compound proposition. It is in the form if P then Q. After if this statement we take it as P. After then the statement is user can access the dashboard, that is taken as Q. So now this given statement becomes if P then Q. And symbolically it is written as if P then Q like this. It is read as if user is authenticated, then user can access the dashboard. For this we have to write the converse statement. So converse will be if Q then P. Right. After if you have to insert Q, after then you have to insert P. So converse statement will be, if user can access the dashboard, then user is authenticated. And inverse statement is, if not P, then not Q, is called the inverse statement. If user is not authenticated, then user cannot access the dashboard. Next is contrapositive statement. It is not Q, then not P. If the user cannot access the dashboard, then user is not authenticated. So here we have 4 statements. We can write the truth table for them like this. So components are P and Q for all of them. So first we write the 4 possible truth values of P and Q like this. Next we'll fill these not P. Not P means 0 becomes 1, 0 becomes 1, 1, 1 becomes 0, 0. Not Q will be 1, 0, 1, 0. If P, then Q. So here it will be 1, 0. Here it becomes 0. In rest of the cases it is 1. This is conditional. This is conditional given statement. And Q then P is converse. While writing Q then P, we have to read Q column first, then P column. So here it is 1, 0. It becomes 0 here. In rest of the places it is 1. Not P, then not Q. This is inverse statement. This is inverse. So third and fourth column we have to combine using if then statement. So 1, 0. Here it becomes 1, 0 becomes 0. Not P, then not Q. In other rows it is 1. And this is contrapositive. Contrapositive is not Q, then not P. So read this column and this column. First not Q, then not P. So where it will become 0? Here. 1, 0. It will be 0. In other rows it is always 1. So what we notice from this is the given conditional has the same truth value as that of its contrapositive statement in every row. In the first row 1 is there, here also 1. Second row 1, 1. Third row 0, 0. Fourth row 1, 1. So we say these two statements, they are logically equivalent. Because they have same truth values in each row. So now we'll define what is logical equivalence. Two propositions U and V are said to be logically equivalent if they have the same truth value written as U logically equivalent to V. The symbol used is this equal to sign with arrows pointing both sides, or you can use 3 parallel lines like this. So generally these two symbols are used for logical equivalence. So P says 5 is an odd integer, Q is a proposition, 5 is not divisible by 2. So any number which is not divisible by 2 will be an odd number only. So both P and Q mean the same, but the way of writing is different here. So we say P is logically equivalent to Q. One more example. Negation of P or Q is logically equivalent to not P and not Q. So how to confirm they are logically equivalent? Using the truth table. So first we write the truth values of P and Q. Then here we require negation of P, negation of Q. So I have made two columns here, not P, not Q. Next we have to write P or Q. So 0 or 0 is 0, 0 or 1 is 1, 1 or 0 is 1, 1 or 1 is 1. Next we negate this, negation of P or Q. So negation of 0 is 1, negation of 1 are zeros here. This is left side. Right side we need here negation of P and negation of Q. So P and Q, 1 and 1 is 1, 1 and 0 is 0, 0 and 1 is 0, 0 and 0 is 0. So again what we notice here is in this column and in this column the truth values are same in each row. So we say they are logically equivalent. It is something similar to actually it is De Morgan's law. For set theory already you know A union B its complement is logically equivalent to A complement intersection B complement. Union becomes intersection here. Here OR becomes AND. Here we are taking sets, but here propositions we are using. So this is De Morgan's law for the propositions. So logical equivalence can be proved using either truth table like this or using the laws of logic. There are 10 laws of logic. You should remember all these. First one is commutative law. Commutative law, associative law, distributive law, De Morgan's law, law of double negation, absorption law, idempotent law, identity law, inverse law, domination law. While proving the logical equivalence using laws of logic, all these 10 laws have to be remembered. Please take a screenshot of this if you want. There are 3 more important laws regarding the conditional. If P then Q is logically equivalent to its contrapositive statement, not Q then not P. Earlier we have seen this. This is very important one. Next is if P then Q is logically equivalent to negation of P or Q. We use this whenever we don't want the conditional statement. To convert this into OR, we can replace if P then Q by this statement. Now if you want to take the negation of this statement, not P then Q will be negation of the right side. So here we apply the De Morgan's law. Negation of P becomes P, double negation. OR becomes AND, negation of P. So even these 3 have to be remembered. Very often we use these results. Prove the logical equivalence of this compound statement given here by using truth table and also using without truth table. It means using laws of logic. So for the same proposition, I will show both the methods. First, using truth table, we have three primitive propositions P, Q, R. P has two truth values 0 and 1. Q has two truth values 0 and 1. R has two truth values 0 and 1. So totally we have 2 to the power 3, that is 8 possible truth values for P, Q and R. So we need 8 rows in the truth table. So these are the first 3 columns. Here I have written all possible 8 truth values of P, Q, R. So always write in this order only, in this pattern only, so that you won't miss any truth value row. Next, what is required here? Negation of P, negation of Q. So P is 0, 0, 0, 0, 1, 1, 1, 1. So when you take the negation of this, it becomes 1, 1, 1, 1, 0, 0, 0, 0. The negation of Q will be 0, 0 becomes 1, 1, 1, 1 becomes 0, 0, again 1, 1, 0, 0. So combine these two using AND. 1 and 1 is 1, 1 and 1 is 1. All these have either 0 in one column, so it will always be 0. Sorry, it is OR, right? For OR, if any one of them is 1, then it is 1. 1, 1, 1, 1. Here both last 2 rows both are 0, so here it will be 0. Next, P and Q and R. For AND, any proposition should not have 0. Otherwise it becomes 0. So only in the last row all of them are 1. In all other cases it will be 0 only. Okay. Now I denote this by A, this as B. We have to combine them using the conditional here. So A then B. So where we will get 0. For conditional 1, 0 becomes 0. Here also 1, 0 becomes 0. 0, 0, 0, 1, 0. 0, 0 is 1, 0, 1 is 1. Now we'll see P and Q. So combine these two using AND. So 0 and 0 is 0. 0 and 0 is 0. First 2 columns you observe. 0 and 1 is 0. 0 and 1 is again 0. 1, 0 is 0. 1, 0 is 0. 1, 1 is 1. 1 and 1 is 1. So these 2 columns have same truth values. I am highlighting these 2 columns. This is left side of the equivalence. This is right side. In each row they have same truth values. So we say these are logically equivalent. So this is using truth table. Now using the laws of logic, same thing can be solved. We start with left side proposition here to here and arrive at the right side. So LHS is not P or Q, then P and Q and R. When we have conditional, we have two options to change to another one here, either this one or this one. So if you change as in one, again you will get a conditional statement that is not going to help us. So I use the second one. If P then Q can be replaced by negation of P or Q. So here I have, this is like A and this is like B. So here we have, instead of A and B, I will take U and V. So U, if U then V can be changed to negation of U or V. Okay. Next, in this one, I can apply the De Morgan's law. Negation of P or negation of Q. If you take the negation outside, what remains is P and Q, because OR becomes AND here. So in the next step, I have double negation. Negation of P and Q, OR. And in this one, I have associated P and Q and put it in the bracket and R. So I have to justify every time which law I have used. I have used here De Morgan's law and associative law. P and Q are associated here. So in the next step, by double negation, negation of P and Q becomes P and Q only, or P and Q and R. So this part I have not changed. So here we have to write by law of double negation. Now can you guess which law we can apply here? It is of the form A or A and B. This is nothing but A itself. So this is like A or A and B. So by absorption law, A or A and B is nothing but A. So in our case, A is P and Q. So we got the right side proposition. Hence they are logically equivalent. So every step which law you have used, that we have to write. Next is rules of inference. Inference means drawing some conclusion based on the given statements. So first we will understand what is an argument. A compound proposition of the form P1 and P2 and P3 and so on and Pn, then Q, is called an argument. So it can also be written in another way, in a vertical form, P1 and P2 and Pn, then one line we draw, therefore Q. So this Q is actually conclusion. This is conclusion. And P1, P2, Pn, these are called premises. And Q is called the conclusion of the argument. So always in an argument, the premises are always taken to be true. We always assume all of these given premises are true. They are like inputs. Q is the output. So given these premises, whether it will lead to the conclusion correctly or not, that we check here. If the conclusion is also true, then we say this argument is valid. If it is false, then we say the argument is invalid. I hope you are getting this. So these premises will be given and conclusion will be given. So it means an argument will be given. We have to check whether it is valid argument or not. So valid argument means an argument is said to be valid if whenever each of the premises P1, P2, Pn, all of these are inputs, is true, then the conclusion, which is output, is also true. Here Q may be true or false. If it is true, then we call it as a valid argument. If it is false, we call it as invalid argument. Now how to check whether the given set of premises and conclusion, the argument is valid or not. Already certain rules have been framed and they have been checked. If the given premises and conclusion are in this form, then we can conclude the argument is valid. The first rule is modus ponens. It is method of affirming. So first premises is P1, which is if P then Q. Second premises is P2, which is P, and therefore the conclusion is capital Q. In this case it is Q. So if you have a structure like this, then you can immediately say, as per modus ponens rule, the given argument is valid. Now the question is, why we have to accept this as a valid argument? See, P1 has to be true, P2 has to be assumed to be true, and this may be true or false conclusion. Okay, if it is true, then only we say it is valid argument. Now this is valid or not, let us check. So here we have P, Q, if P then Q. So here it is given if P then Q is true and P is true. So P is true, it is given if P then Q is true. Now what about Q? It has to be true or false. If it is 0, then this becomes 0. It cannot be 0, right? It has to be, because 1 0 becomes 0. It is very important result. Many times I am repeating this. So this is P1, which is true. It has to be true. And this is P2. We assume this also be true. Now here what it should be? Q. It has to be true because even Q has to be true. If it is 0, 1 0 becomes 0. In the truth table of conditional statement, if you see, 1 0 becomes 0. So Q cannot be 0. Q has to be 1. So 1 means the conclusion is also true. Hence it is a valid argument. So every time you need not check this. Already these rules have been provided. Referring to them, you can directly tell the given statements are leading to the correct conclusion or not. Second rule is modus tollens, which is method of denying. So here one premises is P1, which is if P then Q. Second one is not Q. So we have to assume both of them are true, right? And the conclusion is, therefore the conclusion is not P. Even this will not P will be true. So as per modus tollens, if the structure is like this, we have to say the given argument is valid. Third one is rule of syllogism. First premises, that is input, is if P then Q. Second is if Q then R. From these two, P1 and P2, we conclude the conclusion will be if P then R. It is something like transitive law in the relations topic. X related to Y and Y related to Z. It means what? X is related to Z. P then Q, Q then R, so P then R. So these first three are very important rules of inference. Other three rules are rule of conjunctive simplification. P and Q implies P. So whenever P and Q is true, P has to be true here because both have to be true. Fifth one, rule of disjunctive amplification. P implies P or Q. If P is true, P or Q will be true. Because for R, any one of them is true, it will be true. Rule of disjunctive syllogism. P or Q is the first proposition premises and P2 is second premises and the conclusion is Q. Test the validity of the following arguments. If you have a valid password, then you can log on to the network. Is one premises, P1, one input. Second input is you have a valid password. So from P1 and P2, whether you are going to conclude, you can log on to the network. This all together is an argument. It may be valid or invalid. So does this argument sounds you correct? Sensible? It looks correct, but how do we check this one? So here, after if we have a proposition, we take it as P. You can log on to the network as Q. So P1 becomes if P then Q. You have a valid password. This is P. Therefore, you can log on to the network. This is Q. Now look at this. P then Q, P, therefore Q. Here it is. By rule, first rule, modus ponens, we can say it is a valid argument. No need to write any truth table or something. You have to quote which rule you are applying to justify. Second one, if you have a valid password, then you can log on to the network. Second statement is you cannot log on to the network. Therefore, the conclusion from these two statements is you do not have a valid password. Slightly I have changed the second proposition. I will come to that here down. Third one, if you have a valid password, then you can log on to the network. Second statement is if you can log on to the network, then you can change your password. From these two, the conclusion is if you have a valid password, then you can change the password. So totally how many, in all these three examples, we have three propositions. P is you have a valid password. Q is you can log on to the network. R is you can change the password. So first argument reads like this. It is if P then Q. Second statement is P, therefore Q. So this structure is just like a modus ponens. So by modus ponens rule, the argument is valid. Now second one is if you have valid password, you can log on to the network. You cannot log on to the network, therefore you do not have a valid password. So it sounds correct. It is correct because by modus tollens rule, the argument is valid. Third one, if you have a valid password, you can log on to the network. If you can log on to the network, you can change your password. The conclusion is, if you have a valid password, you can change your password. So it is rule of syllogism. If P then Q, if Q then R. The conclusion is, if P then R. So by rule of syllogism, the argument is valid. So in this example, test the validity of the argument. If there is strike by students, then the examination will be postponed. The examination was not postponed. This is second statement. From these two statements, the conclusion given is there was no strike by students. Now how do we check this, whether this is a valid argument or not? So we take this one as P. There is a strike by students as P. Then the examination will be postponed if then premises, first statement. Second one, the examination was not postponed. So P2 is examination was not postponed, negation of P. And the conclusion here conclusion is there was no strike by students. It means negation of P, not P. So which rule you apply to say whether it is valid or invalid argument? If P then Q, not Q, conclusion not P. This one. If P then Q, not Q, then not P. So by modus tollens rule, it is a valid argument. Okay, last topic is methods of proofs and disproofs. So there are three methods to prove a conditional if P then Q. One is direct method, second one is indirect method, third one is contradiction method. So first we'll see the direct proof. To prove the conditional P then Q, so first we have to assume, the hypothesis is nothing but our assumption. We want to show here if P then Q is true, this final one. So we start with assumption P is true. Then in the second step, we analyze with some known facts and come to the conclusion that Q is also true. Then if you know the truth table of if P then Q, this is important one. 0 0 is 1, 0 1 is 1, 1 0 is 0, 1 1 is 1. So we start with P as true and arrive at Q as true. Hence if P then Q will be true. So hypothesis, first step is assumption. First we assume P is true. Analysis, employing known facts, infer that Q is true. And the conclusion will be the conditional is true. This is direct way of proving. Sometimes what happens, we cannot prove directly very easily. In that case, we try indirect proof. So in the indirect proof, instead of giving the direct proof for if P then Q, we give the direct proof for its contrapositive statement, not Q then not P. Why? Because we know if P then Q is logically equivalent to not Q then not P. So instead of proving this statement, we prove this statement using direct method. So second step, give the direct proof for not Q then not P instead of this, which is as good as if P then Q we are proving. So how to go about this proof? How to give direct proof for this? We have to assume not Q is true hypothesis and analyze and infer that not P is true, then this conditional becomes true. In some problems, direct method and indirect method doesn't work. That time we try the contradiction method. So in the contradiction method, the given statement we assume it is false. That is, we don't accept that whatever they are saying is not correct. So assume P then Q is false. So when it becomes false? When it becomes false? When P is true, Q is false, this becomes false. Right. So starting with Q is false, in the analysis part, we arrive at P is false, which will contradict our assumption that P is true. You understand this clearly? In the hypothesis, we assume the conditional is false. When it will become false, P is true, Q is false, it becomes false. So start with Q is false and you will arrive at P is false, which will contradict our own assumption that P is true. We started with P is true, right? So why this contradiction is happening? Because our assumption itself is not correct. Because we didn't accept that the given statement is true. We denied it. That is why this contradiction is happening. So finally, what should be our conclusion? Our conclusion should be the given statement must be true. So while solving the problems, you need to keep this in mind. An integer n is even if we can write n as a multiple of 2. K is some integer, positive or negative. Any number multiple of 2 is called even number, or any number which is divisible by 2 is called the even number. Similarly, an integer which is not divisible by 2 is an odd number. Odd number we can always represent it as n equal to 2k plus 1 for any integer k, positive or negative. Here is one example. Prove the following statement. For any integer n, if n square is odd, then n is odd. So this part we take it as P. P is n square is odd. N is odd is Q. So given statement reads as if P then Q. So this statement we have to prove. We will try all the three methods. So first is direct proof. In the direct proof, we assume P is true and arrive at Q is true. Hence the statement will be true. So hypothesis, assume P is true. P is what? N square is odd. Next we have to infer Q is true. So analysis part is n square is odd, we know. N square can be written as n into n. Since n square is odd, it is not divisible by 2. Therefore, n is also not divisible by 2 because n square can be written as n into n. If n square is not divisible by 2, n will also be not divisible by 2. So it means what? N is odd. N is odd means Q is true. So we started with P is true. We got Q also true. Hence, if P, then Q is true. The conclusion. So here, if you, for odd integer, we have two options here. So why I didn't take this one, 2k plus 1? I could have taken here n square equal to 2k plus 1, because n square is odd we have taken, right? But I have to decide about n. It means what? Both sides I have to take square root. Square root of 2k plus 1, I don't know whether it is even or odd. So this does not work. That is why I have taken another equivalent statement. What is that? N is not divisible by 2. Any integer which is odd is not divisible by 2. So that is why I have taken n square is not divisible by 2. Indirect proof. So in the indirect proof, this is very important step. So this step is very important. You have to write, you have to convert given statement if P then Q to its logical equivalent statement, which is contrapositive statement, not Q then not P. And then try to give direct proof for not Q then not P. So how to go about this? Assume this is true, hypothesis. In the analysis, you infer that not P is true. So then this becomes true. Indirectly, you are proving this is true. So first assumption is not Q is true. Not Q is true means n is not odd. It means n is, if it is not odd, it has to be even. If it is even, it is multiple of 2. So n equal to 2k. Now I have to decide about P. So square both sides, you will get n square. N square will be 2k whole square, which is 2 times 2k square. 2k square is another integer. So it is multiple of 2. So n square is even here. N square is even means negation of P is true. P is n is odd. Not P is n is even. Sorry, n square. N square is even. Not P is true. Since not Q is true by our assumption and by inference not P is true, therefore not Q then not P is true. It means indirectly the statement if P then Q is true. Third one, contradiction method. Assume the statement P then Q is false. That is, it is not true. When it will not become true? When this is 1, this is 0. That is, P is true, Q is false. Then it becomes false. Now starting, I told you, assume P is true, Q is false. Starting with this, you do the analysis and you will arrive at 0 only, which will contradict your assumption. So Q, we are starting with Q is false. It means what? N is not odd. So n has to be even. If n is even, I can write n as multiple of 2 for some integer k. Now n square will be squaring both sides. It will be 4k square or 2 times 2k square. So any number multiple of 2 is even. It means what? P became even here. But n square is odd, that we have assumed. P is true, that is n square is odd. This is our assumption. What here we are getting? N square is even we are getting. Okay. It means P is false. So here we got 0, which is contradicting our assumption. This contradicts our assumption P is true. Therefore, the conclusion is the given statement if P then Q must be true. Lastly, disproof. To disprove any statement, there are two methods. One is contradiction method and another counterexample. Please remember, while proving any statement, you should not give any numerical example, something like this. Don't give any numerical example to prove the statement. It should be general. But while disproving, you can give one example. While disproving, you can give. Disprove the statement, the sum of two odd integers is an odd integer. In contradiction method, we don't give an example. See here, 3 is an odd integer, 9 is an odd integer, 9 plus 3 is 12 is an even integer. This you can give in the second method by counterexample method, but not in the contradiction method. So how to prove by contradiction? The sum of two odd integer is an odd integer. So disproof by contradiction. So we take one proposition P where A and B are odd integers. Q is a proposition A plus B. The sum is an odd integer. We are assuming like this. So A and B are odd means they are 2k plus 1. 2k1 plus 1. B is 2k2 plus 1. Now A plus B will be 2k1 plus 1 plus 2k2 plus 1. It will be 2 times k1 plus k2 plus 1. k1 plus k2 plus 1 is altogether one integer which is multiplied by 2. So it has to become even. But here sum of two odd integer is an odd integer. But here we are getting even. So it contradicts. This disproves the statement. Now second method by counterexample. If you just give one example where it fails, it becomes disproof. By counterexample, let us take A as 5, B as 7. Then A plus B will be 7 plus 5 which is 12 is even. It is not odd. Okay. So here the given statement is disproved. I hope these concepts are clear for you. So this ends the video. If you like this content, please subscribe and share. And also in the comment section, please write which topic you want me to cover. Thank you.